Welcome everybody to Cardiovascular Lecture number 7. This is part 1, How Preload, Afterload, and Contractility Determine Pressure and Stroke Volume. In today's lesson, we're going to begin to consider the factors that determine the pumping performance of the ventricle. And here are your learning outcomes for the lesson. So the mechanical performance of the heart reflects the collective behavior of the 3 billion muscle fibers in the heart. Remember, the basic unit of contraction is the cardiac myocyte. So we're going to have to focus down to the microscopic level. The basic unit of contraction, the cardiac myocyte, is shown here. Remember that the myocytes are long, slender cells that branch and connect through these intercalated discs with gap junctions, so they're electrically connected. Your recent histology lecture has already introduced the cardiac myocyte and the structures that couple excitation to contraction. Remember that contraction is initiated by an elaborate system that, in response to an action potential, delivers calcium to the contractile proteins rapidly and uniformly. And so the key player is intracellular calcium. Now, here is an isolated cardiac myocyte. It's in a dish. It's loaded with a fluorescent dye called Fura2 that allows us to visualize the concentration of free calcium inside the cell, in the cytoplasm. Now, orange is color-coded to represent high elevated calcium. The cell is stimulated periodically at the top here on one end of the cell with a depolarizing current. And note that as an action potential is propagated down the myocyte, a wave of calcium spreads through the cytoplasm. And note that calcium is removed from the cytoplasm just as rapidly. Of course, associated with this wave of mobilized calcium is a localized wave of contraction. So the cytoplasm is rapidly flooded with calcium, which is then quickly drained away, and this produces a cycle of contraction and relaxation. The key players in this calcium delivery system are the T-tubule and the sarcoplasmic reticulum. T-tubules are invaginations of the plasma membrane that penetrate deep into the myocyte and, as you see, come in very close proximity with the sarcoplasmic reticulum. The SR is a highly specialized endoplasmic reticulum. It is a spaghetti-like network of intracellular membranes that are designed to store calcium. And these SR tubules, as you note in this illustration, weave around all of the myofibrils and come in close proximity to the contractile proteins. So here is how these two players work together in the process of excitation-contraction coupling. First, note that the T-tubule membrane comes in close proximity to the SR that's loaded with calcium. In response to an action potential that propagates down into the T-tubule, the L-type calcium channel becomes activated. Remember, it's a depolarization-induced channel. And this L-type calcium channel admits a small amount of calcium into this restricted space, which then interacts with another calcium on the SR, opening that channel, admitting a large amount of calcium out. Now, it used to be called the ryanodine receptor, and in some texts you'll still see it labeled that way. The reason is because it was biochemically isolated by using a column that had a ryanodine molecule attached to it. The channel binds to that molecule, ryanodine. So a large amount of calcium is then released into the cytoplasm surrounding the myofilaments, and the binding of calcium to troponin triggers contraction by the myofilament. The calcium is then rapidly released from the troponin, causing relaxation, and that calcium is then vigorously taken up back into the SR by the sarcoplasmic reticulum calcium ATPase, or the SERCA calcium pump. Cardiac and skeletal muscle fibers use entirely different strategies for varying their force of contraction. They have to. In response to a single action potential, which is very brief, only 3 milliseconds, the calcium in the skeletal muscle fiber rises to about 10 micromolar. And this level of calcium activates all of the myofilaments to a maximal extent. So in skeletal muscle, all myofilaments are saturated with calcium and reach full activation on each contraction. Okay, if this is so, then how does a skeletal muscle vary its force of contraction? Since the action potential in the motor neuron is only 3 milliseconds long, you can summate many action potentials to achieve a greater contraction. So temporal summation of multiple action potentials can evoke a contraction of greater force. Second, more muscle fiber units are recruited into the contraction, and this is called spatial summation. Heart muscle is much different. Remember, the cardiac action potential is much longer, 200 milliseconds versus 3 milliseconds in the motor neuron. And as a consequence, the action potential overlaps with the resulting contraction. Because these action potentials are so long, there can be no temporal summation. And recall that all cardiac myocytes are electrically coupled by gap junctions. And because all fibers of the heart are excited during each contraction, additional fibers cannot be recruited. There cannot be any spatial summation. Now, the heart overcomes this shortcoming in a very clever way. In a cardiac muscle fiber, a single action potential causes intracellular free calcium to rise to only about 1 micromolar. And this amount of calcium is sufficient to produce only a partial contraction. And so contraction is graded, it's variable, it is submaximal. And this has important consequences. Not only is the contraction graded, but it depends on many factors. First, several neurotransmitters, hormones, and drugs can alter the level at which calcium rises in response to stimulation. Note how norepinephrine, for example, shifts the sensitivity of the contractile apparatus so that it is more sensitive to a given level of calcium. And second, stretching the muscle fiber also markedly increases calcium sensitivity. So the heart varies its force of contraction by adjusting the amount of calcium delivered to the contractile proteins and the sensitivity of the contractile proteins to this calcium. In contrast, skeletal muscle changes its force of contraction by, remember, recruiting more fibers and by receiving more frequent impulses. So this is an interesting graph which shows how the action potential, intracellular calcium, and contractile force change over time in relation to one another. Notice that membrane depolarization evokes a steep rise in intracellular calcium, and after a brief delay, the fiber responds with contraction. And look how norepinephrine shifts this response. The action potential is shorter. The intracellular calcium burst is larger and shorter, and the consequent muscle contraction is stronger and shorter. So let's return to the T-tubule and the adjacent sarcoplasmic reticulum. The source of calcium that initiates the contraction of the heart is now well established. Only 15% of the calcium comes from outside, and this is called activator calcium. The other 85% is released from the SR into the cytoplasm internally, and this is called the calcium spark. So if we place a heart in a solution lacking calcium, it will immediately stop contracting. Why? Because the activator calcium that is admitted into the cell during depolarization by the L-type calcium channel is needed to trigger the much larger release of calcium from the SR. And this larger pool of calcium is what activates the myofilaments. Now that we've caused the muscle to contract, how do we get it to relax? After contraction, calcium is released from the troponin into the cytoplasm, and it is vigorously taken back up into the SR by the circa calcium pump. So most of the calcium is resequestered back into the SR from the calcium pump from which it came in the first place. A smaller amount of calcium equal to the activator calcium is returned to the extracellular space by a sodium-calcium exchanger. This exchanger, located in the plasma membrane, trades 3 external sodium ions for 1 internal calcium. So it harnesses the large inward sodium electrochemical gradient to extrude calcium from the cell. Notice that this exchanger moves 1 net positive charge into the cell, so the internal negative membrane potential augments the thermodynamic driving force for calcium extrusion. And finally, any residual calcium remaining in the cytoplasm may be expelled by the low capacity, high gradient calcium ATPase pump. Okay, and now we come to a very important concept in this lesson. There are only two ways that cardiac muscle can increase its contractile force. We've already seen one. That is to change the initial fiber length. When heart muscle fibers are stretched, they tend to contract with greater force. And this is called the Frank-Starling mechanism. We'll talk about that in greater detail. The second way is for the cardiac muscle fiber to change its contractility. That is, at the same initial fiber length, various hormones can alter the contractile force or inotropy of the fiber itself. For example, if we measure the force of contraction at the same initial fiber length, no stretching, and add norepinephrine, we get a much stronger contraction, which is also shorter. So we're going to examine the molecular mechanisms underlying these changes for both a change in fiber length and a change in contractility. It's important that you do not confuse contractility with the Frank-Starling length tension effect. We'll get to that in a moment. Now, the Frank-Starling law of the heart, the length-tension relationship, was described in the early 1900s, not by a guy named Frank Starling, but by two guys working in collaboration. Otto Frank, a German physiologist, and Ernest Starling, an English physiologist. Starling was a very illustrious figure in physiology. He is the guy who introduced the term hormone. He also described the distribution of fluid between blood and tissues, which we'll talk about later on in Block 2. And with Frank, he described the effect of ventricular volume, fiber length, on pumping performance. And that has become known as the Frank-Starling law of the heart, or the Frank-Starling length-tension relationship. Let's perform the same experiment that Frank and Starling performed. Suppose we dissect out a single heart muscle fiber. Let's say it's a papillary muscle. And we attach it to a rack whose length can be varied by adjusting this knob. In other words, the degree to which the muscle is stretched. And on the end of the rack, we have a force transducer that can measure the tension developed by the muscle. We start our experiment with the muscle completely limp, no tension, and then we begin to adjust the knob to increase the length of the muscle. In other words, to stretch it out. And as the muscle as a whole stretches, the sarcomeres begin to pull apart. So when the resting muscle is stretched stepwise, it will stretch easily initially because it has elasticity, it is compliant, it has capacitance. But just like a strip of dead meat, it will offer tension as it's stretched further. We reach a length out here at which the elastic elements of the muscle become taut, and the tension rises sharply as we try to stretch the muscle further. And now we repeat the experiment, but this time at each fiber length, we stimulate the muscle with an electrode, and we get this green curve here. That's the total tension, and it is the sum of active tension plus passive tension. So if we strip out the passive tension of the resting muscle from the tension developed by the stimulated muscle, we get the active component. Note that the muscle contracts with much greater force when it is stretched up to a certain point. And it turns out that the cardiac myocyte operates normally in this range here. So a little bit of stretch results in a much more vigorous, forceful contraction. Research has shown that there's at least two factors which explain this phenomenon. First, stretching the muscle improves the overlap between the interdigitating myofilaments. And since more actin-myosin cross bridges can participate in contraction, more tension is developed. At some point, the muscle is overstretched and the actin and myosin filaments are pulled apart from one another, and less actin-myosin cross bridges can participate in contraction. Second, when the fibers are stretched, the thin actin filaments somehow become more sensitive to a given level of calcium. So more cross bridges can form at a given concentration of calcium, probably because the affinity of troponin C for calcium is somehow enhanced by muscle stretching. And as a result of these two phenomena, stretching the muscle results in a stronger contraction. Again, when overstretched, The muscle contracts with less force, probably because overstretching reduces the necessary overlap between the myofilaments. Do we call this a change in contractility? No, this is the length tension effect. So how does this relate to the heart? Remember, the walls of the heart are made up of billions of small myocytes, and as the ventricular cavity fills during diastole, the heart expands, and the little myocytes will all stretch out to varying degrees depending on the end diastolic volume. The degree to which the resting ventricle is filled during diastole is dependent on the preload. Remember, the sum of forces that fill the heart. So let's go back to our length tension relationship during systole and diastole and relate it to the heart. Within physiological limits, the tension generated by the contracting heart becomes greater as the heart muscle is stretched. Now, the initial myocardial fiber length varies in proportion to ventricular filling during diastole, or the end diastolic volume, and the EDV is in turn determined by the preload. On the y-axis, we'll plot the active tension that the muscle is capable of generating when excited, the ability to develop ventricular pressure. A graph like this, which plots the pumping performance of the ventricle as a function of ventricular preload, or end diastolic volume, is called a ventricular function plot. So if end diastolic volume, ventricular muscle stretch, is an important determinant of pumping performance, what in turn determines preload? Recall that preload is the sum of the three forces that promote ventricular filling. And this is atrial pressure, in other words, the pressure of venous return at the level of the atrium that on opening of the AV valves allows the ventricle to fill. The second force is ventricular recoil. As the ventricle relaxes and expands, a suction develops that pulls the blood in from the atrium. And finally, after most of the ventricle is filled passively, at the end of diastole, the atria will contract and provide an extra boost to ventricular filling. This is called atrial kick. So atrial pressure plus ventricular recoil plus atrial kick determine the final preload. And as a quick recap of the Frank-Starling length force or length tension relationship, if the ventricle is subjected to greater preload, muscle fibers are stretched, myofilament overlap is improved, and they become more sensitive to calcium. This makes the subsequent contraction more forceful, faster, and, by the way, consume more energy, which we'll talk about later. So let's go back to our ventricular function curve. Remember, it tells us how much pressure the ventricle is capable of developing when filled with a given amount of blood. In other words, when expanded by a given end diastolic volume. Remember that when we plot the ventricle's pressure against its volume, the cardiac cycle can be represented as a PV loop. Under normal circumstances, the ventricle fills with about 65 mils of blood, starting at maybe 50 mils residual volume, the end systolic volume, and through diastole fills with about 65 mils of blood. And at that degree of stretch, when the ventricle contracts, it has the ability to pressurize the blood to maybe 190 or 200 millimeters mercury. However, as soon as the building ventricular pressure exceeds the aortic diastolic pressure, the aortic valve will open and the ventricle can eject. At the end of ejection, the ventricle returns to the end diastolic volume dictated by the intersection of the ventricular function curve. Why? Because at that degree of stretch, the ventricle can only develop 120 millimeters of pressure. We then enter the ventricular relaxation phase to return us to a new cardiac cycle. So this PV loop would model a normal cardiac cycle with a stroke volume of about 65 mils. And what if on the very next beat, the ventricle was subjected to a greater preload, more blood filled the heart, and the ventricle now stretches to a greater degree to accommodate that extra volume. Now the ventricle is able to develop a much larger pressure, but as soon as the pressure rises to the aortic diastolic pressure, it begins to eject. And now the PV loop shows that we have a larger stroke volume produced by a larger filled volume. So when the heart is presented with more blood, it will eject the extra blood on the very next beat. And this is how stroke volume is matched to ventricular filling. In other words, this is how cardiac output is matched to venous return. That's very important. It's also important to recognize that preload varies from beat to beat with fluctuations in venous return, and that's modeled here. What causes preload to change from beat to beat? Changes in breathing, changes in sympathetic tone, changes in posture, changes in skeletal muscle activity. We're going to talk about each one of these, but let's focus first on breathing and sympathetic activity. The heart receives blood from the great veins in the thoracic cavity, the superior vena cava and the inferior vena cava. The left heart receives blood from the pulmonary vein, so only the blood within the large veins of the thoracic compartment is immediately available to fill the heart. So the volume of blood presented to the atria has a certain pressure that depends on the volume of blood in the veins. And we call this critical pressure the central venous pressure. That is an important determinant of the rate and extent to which the heart fills with blood during diastole. Remember, one of the most important components of preload is the atrial pressure, the central venous pressure that fills the heart. So there are really two functional pools of blood in the body. The blood in the thoracic veins, that blood is immediately available to refill the heart. Remember, this is the central venous volume, and that refilling is sensitive to fluctuations in intrathoracic pressure, which vary with breathing and posture. So the thoracic compartment is one pool of blood. The other pool is blood outside the thoracic compartment, or the peripheral compartment. The blood in the peripheral veins is not immediately available to refill the heart. However, sympathetic constriction of the large veins can squeeze on the veins in the periphery and mobilize that stored blood from the periphery back to the heart. So blood can be shifted from the peripheral compartment to the thoracic compartment in order to augment the filling of the heart, and this is all controlled by the sympathetic nervous system, which we'll talk about later. We'll also learn that preload is abnormally increased in several pathological states: hypervolemia, leaky heart valves, and heart failure. And that concludes part 1 of lecture 7. Please stay tuned for part 2, just a short video.